All right, good afternoon. All right, good afternoon. Okay, let's get started. All right. Okay, so last time we basically wrap up chapter 2. We had a summary posted there, and so that will be the content covered in the first exam that's coming up next week. All right. The location, we haven't finalized a room yet, but I will let you know hopefully by Monday or Tuesday. But the time will be the same time, so don't worry about it. It's scheduling. You may go to a different room there. That's it. Okay. Okay. So today we're going to start talking about chapter 3, and that is torsion. All right. So before we talk, if you have a bar, right, you're applying axial load, you're pulling on it or you compress on it, it will elongate or shrink. We can know how much you can get deformation, right? And also you know how to do the calculated stress. Okay, so today we're going to talk about torsion. That is when you have a bar that is under a moment. So when you have a bar like this, you apply movement at the end, like you screwdriver, you tie the screw, and that basically you apply a torque to this, to the screwdriver, right? And this kind of situation we call torsion, because you are twisting something, it deforms. All right. So we all know what's a movement, right? You all know what's a movement. Okay. So here is actually so what's a movement? Force times the distance, right? Okay. So let me jump to the next slide, then we can actually look at the picture here. Okay. So when you have a force that applies somewhere, and then if you look away from that action line, so the force times that distance will give you a movement, right? Or in general, if we just say I apply movement, what that mean? That means I can apply a pair of forces, right? So a pair, and that opposite direction, same magnitude, but they are not along the same line. Then you're going to generate a moment. So that's a moment. Right? Okay, so a moment is basically the force times the distance. That's the distance between the two action lines. All right. Okay, so in this chapter, one thing similar to what we just learned in chapter 2, structure-wise, we're going to learn how to calculate when you have a bar and a torque, what kind of deformation you're going to get, and then what kind of stress you're going to have, and then when you have a non-uniform bar, what's going to happen, how you calculate the stress and the deformation. Then indeterminate problem will come up again. So we're going to use the Fed.com in this situation here again. That's why we put the Fed.com there, because you're going to use it again and again. All right. And then we're going to talk about the stress and the strain energy. So that's the overall structure for chapter 3. We're just repeating the same kind of practice as chapter 2. It's just a load is different. Load now is a torque, not a force anymore. All right. Okay, so one point I want to emphasize here is when you have the picture on the left, right? So this one here is F, the moment is F times D, because D is actually the distance. But for this one, you cannot just calculate the moment by F times D, because D is not the distance, right? So D is the distance between the two action points, but not the action line. So therefore, in this case, you have to find out the vertical distance. All right, so let's go to the next one. Okay, so this is the situation we're going to have. If you have a torque applying to a bar, right? We know this is going to happen, right? If I apply, so this end, if you fix this end is relatively going to rotate an angle. That's to be the kind of deformation. Right? So the load will be torque T. And a torque, we use a double arrow to label it. Or you can use a curved arrow. Right? That's the same as you learn in statics. You can use a curved arrow, show this a moment. Or you can use a double arrow, show that's a moment. Right? Okay. So our task for now basically is to find out when I know I'm applying a torque T. This is known, a load. Now, how much rotation I'm going to generate in this bar? That is the task. Okay. So first, if you look at this picture here, you can see here, right? So the things are rotating, right? Most likely in the middle. Let's say in the center of this shaft, this bar, right? This bar actually and the torque, we call it the shaft. So just shaft is basically the bar and the torque, actual torque, right? Torque is pointing along the actual direction. So in this bar here, when you apply a torque, we call shaft. In this shaft, there will be rotation. But if you look at the center line, most likely the center line will still remain as the center line, right? In other words, the deformation most likely will not be uniform. It's like when you rotate a disc, right? When you rotate a stack of a card, when you rotate them, you can see each one can be different. So the center actually remain there, not moving. But on the edge, you can see it's moving, the distance there. So what does it remind us? That says the deformation in this thing now is not uniform anymore. So maybe the stress will be not uniform. So therefore, you cannot do something like a P over A, give you average stress. You cannot do that way. You cannot say T over something give you the deformation angle phi. That won't be true anymore because now we don't have uniform situation. So it's a little bit challenging now. All right. So how can we find out the actual deformation? The way we can do it is actually look closer to the deformation pattern. See how things deform. Okay, so here is one model. Actually, I have one actual. Anyone want to hold it? So I can only stay here. All right. Oh, sorry. Right on target. Okay, so all right, sorry. So when you have this bar here, I used to have a lot. Somehow some student took it, so I only have 2 left now. I'll buy a few more maybe next year. Okay, so this I just got from Home Depot. You know, we use this a lot to wrap up the pipes, right? So it's very cheap. Don't cost much. Okay, so here is basically a bar, a shaft, right? If I rotate it, now I want you to look at the line here. I draw a few lines here. Okay, look at the lines. How does the line change? If I just rotate a little bit, can I say the line pretty much remains straight? Doesn't change, right? So that's the kind of pattern what you want kind of set up in your mind. Okay, so it's like you have a stack of cards. We all play cards, right? Or like a book, if you twist it, right, on the top, then they will just relatively move. But if you look at each one of them, they remain just this way, just rotate a little bit, right? So each disk here actually remain as flat. So based on this observation, what we're going to do is actually we assume, right, the planes in this object, in this shaft, will remain as a plane. So we're going to have what we call plane assumption. All right. So what's the plane assumption? We assume when you have a shaft under torsion, the cross sections, they will remain as a plane. They just relatively rotate a little bit. Okay. It's not just remain as a flat plane. They also don't change their size. So it's like they're rigid. They just rotate a little bit. So each one remain rigid. They just same size, same shape, just rotate a little bit. So that's the plane assumption. Right. Okay, so based on this plane assumption, then we can kind of figure out how things deforming there. What's the strain in this bar? And then we figure out when you apply torque, how much deformation you're going to get. Okay, what kind of deformation you're going to have in the bar when you rotate it? When I'm applying a torque here, what kind of deformation you're going to get? Torsion. This kind of a situation we call torsion. But what kind of deformation? How things deform? There will be an angular rotation, right? So therefore, the deformation is basically an angular rotation, right? Or you can say, oh, shear strain, because angle changes, that's a shear strain. So what we're going to need to find out is when I apply a torque T here, how much this point is going to move, to rotate relative to the original position or relative to the other fixed end. And so that will be the what we call a rotation angle. Actually, we have a term, we call it twist angle. So you're twisting this shaft. So we'll find out what's the twist angle if you're applying torque T. That's what we need to find. Okay. And the approach we're going to use is look at the geometry, how things deform, and then find a geometric relation. And then we go from there. All right. Okay, so with that understanding, what we're going to do is look at how locally they deform. Okay, the same trick again. Now we cut a small element, a small segment, say the dx there. So we can cut this small segment here. Look at this segment. Okay, see how this segment is going to deform under torque T. Okay, so first question before I move to the next slide. What's the torque here? If I look at this cross-section inside here, so I can make a cut, right? And then this is the free body diagram. I draw this part. So you have a torque T applying here. Now what's the on this surface? What kind of reaction you have on this surface? You have something, maybe a torque T, let's say T unknown there, right? Okay, what's this value? Can we find out what's this value? Should be exactly the same as you have there at the edge, right? In other words, by equation of equilibrium, we know through this shaft, it's a uniform shaft. Then you have everywhere you have the same torque T. In other words, we say internal torque in this shaft is T. We are applying load T here, right? They're all uniform. It's the same everywhere. Therefore, that's why we can just select one element and then look at it, how it deforms. And then we just do integral. You just add all of them together, multiply the whole length, it gives you the total. Yeah. Yeah, so there are two ways to draw it. One way is as shown here. Another way, I can draw the same torque as, like use this arrow here. So a curved arrow, and that can be the same. No tension. See here, it's movement. Okay. How do you determine a movement is positive or negative? That's a good question. The double arrow is positive if it points away from the surface, following the surface normal. Right? How you define a positive force when you're pulling on it? It's away from the surface, right? Follow the surface normal. Here is again, same. It's just the movement follow the surface normal, or follow the axis. So that's a positive torque. If somehow if you do this way, towards it, then that's a negative torque. Okay, so depend on it's away from the surface you look at it, or towards the surface you look at it. Okay, so for the same reason, now if you look at this one, is this a positive or negative torque? What's the definition? Away from surface is right hand, right? So right hand away from surface, so that's positive. This one away from surface, positive. So they both positive. This is a positive pair. You have to have a positive pair to generate a positive deformation. This is similar to force. You have to have a pair of force generate elongation. Now you have to have a pair of movement to generate a twist. So this is a positive pair. Okay. So when you talk about deformation, they both, the two on both ends, they're positive. When you write the equation of equilibrium, say sigma, all the movement in the x direction equals 0. Then you're going to have a t on the left, and then t on the right. That's why it's all equilibrium. So for equation of equilibrium, one direction is positive, other direction is negative. But for deformation, depend on the surface, that's all positive. So this is a positive pair in terms of deformation. All right? Okay, that's a good question. Any other questions? No. Okay, if not, let's move on, look at the geometry. Now next will be basically look at this small element. All right? So here is a blew up picture of what we just had there. Okay, so if you apply torque, so this element dx, okay, going to have some deformation here. If we fix the left side, use that as a reference direction, reference surface. Then the one on the right going to rotate a little bit, right? Because you know you are twisting. So therefore, from one plane to another plane, you're going to have some rotation there. Okay, so we assume that's what you assume. Okay, over dx, you're going to have a small rotation d phi there. So this is the rotation angle we assume there. Okay, now it's like I have this. So this will be the dx, right? Actually, I used to have a one, just cut this short so you can see. So look at this part. So this part is fixed. I'm holding here, fixed to the wall. And then this part going to under torque, so we're going to rotate this way a little bit and rotate a small angle d phi. Okay, now if you draw two lines here, and that's the line AB and the DC. So this two line, because this is going to rotate a little bit. So therefore, this line won't be flat anymore, right? It will deform to somewhere a little bit angle to this side. And so that's why you're going to have this line AB now become this line here. Okay, so in other words, the point B, going to move to B prime. Right? So that's the deformation or the displacement. So this point actually travel that small distance. Right? Okay, so once you realize this picture, next, the relation actually is pretty easy. It's very simple. Okay, so this B prime, let me just write it here. So the B prime, this is arc length, right? Small arc length. Well, we can say a distance because it's so small. You can call it arc or call it a straight line. Doesn't matter. All right. So this length, I can calculate two ways. One, if I look at this surface here, okay, this angle, I call this angle gamma. So I can say this will be equal to gamma times dx. Do you all agree? Is this at B prime, right? You rotate that much. So the angle you rotate small gamma. So what's the distance you travel there? It's the gamma times my arm length, right? So therefore, you can have this relation. Okay, now what's gamma? Gamma is initially you have A, B, C, D. That's a square. On the surface, you have square. A, B, C, D. Right? Now it's changed to not a square anymore. It turned an angle. Okay, what do we call this angle? You have a square. Now it's turned a little bit. What do we call this angle? What kind of chapter 1? We call it shear angle or shear strain? What's shear strain? Shear strain is if you have a square, right? You have a force that you apply there, and this will tilt to one side, turn angle gamma. So that gamma is the shear strain. Shear strain is the angle change, right? So what we have here is actually the gamma will be the shear strain. The shear strain of this surface block. It will tilt by angle gamma. So that's a strain. Okay, so that's one point. Now, if you look at the cross-section, okay, now let's look at this part. So I'll just draw it here. So this part, oh, somehow I'm miles away. Let's see if I can erase it. I think I'll just leave it there instead of mess it up. Okay, so that's a triangle, small triangle there, right? So how can you write the relation between B prime and the d phi? What's the relation between the B prime, that length, and the small angle d phi there? What's the relation between d phi? Time that distance, right? Okay, what's that distance? It's the radius, r. Right? So from looking at the surface, you have the first part. If you look at the cross-section, you're going to have the second part of this equation. So therefore, we have this relation here. Okay, what does this mean? That means the shear strain gamma is equal to r times d phi dx. Right? In other words, if I know how much this rotation is, then I know what's the strain. The shear strain. Okay, that's the first point. Second, what if I, instead of looking at the surface, what if we cut the middle? If I make it peel it off the outer layer, so then I look at the inside, so then you have a different R, right? The R will be smaller because you peel off the top layers. So if you go inside, R will be smaller. When R is smaller, what changes there according to that equation? Gamma going to decrease, right? So when you go through from inside to outside or from outside to inside, when you change the R, different locations, different layers, you're going to have different shear stress, a shear strain, right? In other words, if you plot it, so the gamma shear strain versus R, you're going to have this relation. At the right in the middle, gamma going to be 0. There's no shear strain. And the very edge, you're going to have a high shear strain. That's the largest, it's at the edge, right? A linear relation, actually. So that proves that deformation is not uniform. In the middle, it's 0. At the edge, it's the maximum, right? Okay, that's how this shaft is deforming if you're applying torque. Okay, with that, this equation, actually everything else next will be easy. Okay, so let's move on. I think we can move on to the next page. Yeah, so here is actually explain that process. So we can skip this one actually. This will show up in the online slide. So you can actually, if you want to read it through, that's fine. You read it later. Okay, so we have this shear strain. I think I explained a little bit easier way today than I used to do. Okay, so we have that. Okay, so this is the pattern we're going to have. So the shear strain going to be 0 in the middle, right? And the largest at the outside, because we know shear strain gamma is R times d phi dx here, right? So it's proportional to the distance R. All right. Okay, so what's theta here showing? So theta actually is defined as d phi dx. It's how much rotation you have per unit length. It's more like a intensity of the twist, right? How much you actually twist something. All right. Okay, so that kind of a deformation pattern, the strain pattern, in other words. All right. Okay. Now, we haven't found out the link between how much angle I'm going to get and the torque I'm applying, right? That's the goal. Remember that? So let's move on. We can find that. Okay, so how can we find it? How can we link from strain? Now we find the strain. From the strain to the moment. Moment related to what? To the forces, right? Force related to what? Stress. Okay, stress. How is stress related to strain? Linear elastic Hooke's law, right? So we're going to have stress, you're going to have shear stress, because this case is shear strain. That must be shear stress. So shear stress will be G times gamma, right? Okay. Now we find out the shear stress. Okay, what kind of pattern will you have for shear stress on this cross section? If I look at here from the center to the edge, how does the shear stress change from inside to outside? It will be the same, right? Straight line. Here is the maximum. Here is a smaller, 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 and then 0. So the shear stress, same pattern, linear distribution. So now we know, okay, not just stress. A strain is not uniform on cross section. Stress is also not uniform. And there are actually a linear relation, right? Inside is 0, outside edge is maximum, and they're straight line. Okay. Okay, now from the strain, we now move to the stress. We found out stress. Now, how can we, from the stress, can we link this to the moment? So here, for example, if I look at this small area here, you're going to have a shear stress. How? If I look at here, you're going to have a shear stress tau. Here, you're going to have shear stress tau pointing this way, right? Here, shear stress tau going to point this way. Now, how can I find the resultant? What kind of resultant would you expect? Let me answer this one first. You think with all this area, so here, everywhere, right, you're going to have shear. This is a little bit bigger. Here is a little bit tiny shear stress. So when you add all of them together, what would you expect? You get a resultant force and a resultant moment, right? Okay, now how much resultant force are you going to get? Would that be 0? Why not? I would say it's 0. Because, okay, whenever I have this part going to have a force here, right? This tau times the area give me a force here, point this way. Now, on the other side, here, I'm going to have an element, same shear stress, but it's opposite direction. So now whenever I have one here, I have another one there. I'll cancel out. So when I add them together, the final result will be 0. Right? So I don't have to mathematically prove it, but I can just kind of understand it by physically, explaining it. Because physically, whenever you have one shear stress here, on the other side of the circle, you're going to have exactly the same shear stress because R is the same. Right? And then you have the same area, so the two forces will be equal. Therefore, the total force will be 0. And that actually only generates a moment, right? A couple generate a moment. So you have all this small, 1 point here, 1 point here, they're all opposite direction. That generate movement, no force. And then another movement, no force, movement, no force, small movement, no force, bigger movement, no force. So when you add all of them together, what are you going to get? 0 force, but a certain movement, because they're all the same direction. Okay, now, so therefore, we just need to calculate how much movement you're going to get. Right? We can actually save one step, not calculate the force. Right? Okay, so this is just repeating what I just said. All right, so, okay, now, let's calculate how much of the moment we're going to get. Okay, how to calculate the moment? Okay, so the moment should be, I think I actually have the equation here. Yeah, so for this small area, it's highlighted here. So the shear stress, we know it's tau. We already have the equation to calculate, right? So when you have a tau there, the moment generated by this small force from this small area will be the force times the distance. So the distance we call diameter, the radius, right? So that's what we call rho. The reason we use rho is just rho can change from 0 to the edge. Right? It's just a letter. You can call it rho or you can call it r. Right? Doesn't matter. Okay, so the force in the parentheses here, this is the force. Because the stress times the area, that's the force. And then times the distance, so that'll give me a moment. Okay, so therefore I calculate the moment generated by the force here is this much. Okay, now how can I get the total? Integral, right? So I can do an integral. So the moment total here will be all the small ones add together over this cross-sectional area A. Right? That's mathematically you can do that. Okay, so therefore you can take this equation there, and so that'll give you this equation. Okay, now we already know what's tau. Right? Remember what's tau? Tau equals to the shear modulus times the shear strain. What's the shear strain? Sorry. What's the shear strain? Gamma, right? Gamma equals to R. Here is rho. We use the letter rho, right? So it'll be rho times d phi dx. Right? Okay, now plug this in. I think this will give you what we have here. Okay. In this part, we call this one theta. So basically it will be g rho theta. It just use theta to represent these two terms. One make it easier, actually. Maybe make it more complicated because you introduce another variable there, right? So depending on your preference, you can use theta here. You just use d phi dx here. It's either way. Okay, now put it in. So we're going to get this equation. Okay, why you get this one? Why can you throw this? Why this g is outside now? Constant throughout. Why theta is outside? It's constant, right? Because on this cross section, you just rotate theta. So for this part, every point, they just rotate the same theta. So actually d phi dx, that's the same. So you can take it out. So what's left inside will be this thing here. Okay. So what is here? What actually is this part? We can call this, give a term. We call it IP. I think it's maybe the next one. Yeah. Right. So IP is something we learn in statics actually. We call moment of inertia. Right? Because it's to the center, so we call it the polar moment inertia. If it's to an axis, we could just call moment inertia. Actually, we're going to use that when we talk about bending. But here, we talk about the inertia to the center, to one point. Right? Okay, so if you're not familiar with this, or you forget what we learned before, you can review the textbook. I think chapter 12 help you review all this thing there. Okay, for now, I think you could just take it for granted. Okay, that's a quantity we learned before. This one, we just call it polar moment inertia. Okay, how to calculate? We'll do actually next. But for now, we just call this term moment inertia. Okay, with that, so the equation can actually be a little bit easier. So you're going to have T equals G theta and then RP. Right? That's for cylinder. We talk about for cylinder, right? Okay, now we can move this a little bit further. So you can calculate the shear stress, or you can calculate the theta. Okay, what's theta? Remember, theta is d phi dx, right? In other words, from here, we actually get this equal to d phi dx. Okay, now, what do we got? We got this torque T. If you're applying torque T, now I can calculate this amount, the ratio of rotations per unit length. Right? For a small segment, 1 unit length, I can calculate how much the angle is going to rotate. It's going to rotate this much. Yeah. Yeah. Okay. So this is the relation, right? So I know how much per unit length is going to rotate. Now, if I want to calculate the total, how do you calculate the total? You add all the segments together. Okay, how do you add it? Integral. So what you have, it will be phi should be integral, right? Of all the d phi over from x equals 0 to L. Is that true? Okay, if that's true, now I know what's d phi here, from here. So I can take it in, so from 0 to L. Okay, d phi is t times dx, then over g ip. Is that correct? Okay, just mathematical derivation, right? Okay, now here is a key concept. Now, okay, what time can I take the t outside, g outside, ip outside of this integral? At what situation? If g is constant, if t is constant, whoever is constant, I can throw it out. So, in other words, if t is constant, g is constant, ip is constant, then I can take all this out. Okay, if I take it out, what's left there? It will be dx from 0 to L. What's that? L. So you're going to have this equation. Okay, so now you understand why we say this equation will only apply to a uniform shaft, uniform bar. Because only when it's uniform, you can take it out. So you have this equation. All right. In general, if it's not uniform, doesn't matter. I just calculate it this way. Do the integral. Okay. But for this class here, we'll make it easier. We talk about most of the time about the uniform shaft, or not uniform shaft, but with several segments, they are uniform. right? Okay, so this is the key equation, but actually this is the key equation because this applies to all the situations. Right? So actually here we can actually talk about two situations. If you have a uniform bar, this is right to be here, the equation. What if it's not uniform? You have here is bigger, here is a bit smaller. What are you going to do? You're going to divide it up. Okay, this part is uniform. I calculate the integral, right? So you have this constant. Now this part is a constant. I can do this integral here. And so what do you end up? This part, then add this part, right? So mathematically, actually, let me see, I can write here. So I can explain, okay, so I can say phi will equal to, right, from 0 to the L1 part. That's the first segment. And then I'm going to have d phi, right? And then plus from the L1 to the L2 part, and the d phi. Mathematically, I can do that way. And then in this part, everything is constant. In this part, everything is constant. So I can throw all this out. So what I'm going to get will be this part will be T1, this part, right? And then the G1 in this part, IP1 in this part. And then what's left there will be the L1, right? And then the second part, I'm going to have T2 constant, take it out. G2 constant, take it out. And then IP2 constant, take it out, right? Left will be an L2 part. Or you can say L2 minus L1, right? Oh. Okay, so basically now, with this equation, we cover two sections of this book, of this chapter already, right? So they are the same thing. You just either just use one equation, calculate all together, because they're all uniform, or you divide it up, calculate each one, add together. That gives you a total. All right? Okay, yeah.
So we're doing different sections of cylindrical, so I'm going to get like conical.
For this practice, for the homeworks, for exams, we're just cylinders. Yeah, just straight cylinders. But in real life, practically, you can have the cross sections that keep changing, right? They give you any kind of function. And then you just plug into this integral equation, you calculate. So concept-wise, it's the same. Just mathematically, it will take more time. And we have limited time, so I won't give you that for exams. All right? But the concept is exactly the same. All right? Okay, any other questions? Okay, if no other question, let's do a little bit example practice. All right. See if I have a blank page here. Okay, I do have one. I'll use this space here. Okay, so let's answer two questions. One is, how do you determine the IP? Second, let's go over one example. Okay, I think we can do that quickly. Okay, how do you calculate the IP? Remember the equation. Integral over the area, rho squared dA, right? And then you just do it. Okay, so the textbook gave you for circular, a hollow tube, a square, or rectangular. Okay, so therefore I leave that as your homework assignment, reading assignment. Read through how they derive the IP values. Okay, the equation actually, I think it's show up here. Yeah, it's actually show up here. So you can say all these equations. All right. So later on, you don't need to go through that derivation process. You just find out this and use it. You know, from a menu. Even later on, you go to work, right? So when you are in a engineering practice, so you just find a menu and then find this equation. Or actually, after a while, you will actually somehow will memorize it because you use it a lot. Then you're going to memorize. All right. Okay. So one thing I want to remind you here is, for the hollow tube, it's 4 D24 minus D14. It's not the D2 minus D14. Okay, this is wrong. Because sometimes people write this way. Okay, just pay a little bit attention, that's it. Okay, now let's go back to user space, go over one example. Okay, now if I have this bar here, okay, Now I'm applying a torque T. Okay, not applying force anymore. Now I'm applying torque. Okay, I know all the parameters. So I know the E material. Actually, now I need the G, right? So it'll be the G. And also, I know the length, right? Total length, let's say is L. And now I also know the cross-sectional area, the shape. So basically, I know IP. Actually, A doesn't matter anymore because I need IP in the calculation. Remember this equation? Phi will depend on T, L, G, IP. So now IP replace A in the equation. Remember we used to have delta equal to N, L, E, A. So they're very similar, right? Okay, so here's my question. For this bar, I'm applying a torque T here. So you change, somehow find out, okay, the angle turned at 2 degrees. That's what I find out. I do the calculation, I find out, okay. Now, what if I apply 2T to this bar? How much angle going to get? Use this equation, right? Okay, so I'm going to have phi equals to 4 degrees, all right? Okay, now, second question. If I apply T, all right, to the same bar, okay, but now actually I changed the bar a little bit. I made the bar, the R, change to half the radius. How much angle I'm going to get? It's by half, 4 times more. First, it's more or less? Going to rotate more or less? Okay, that's the, yes, that's a, definitely will rotate more. Because smaller, its IP will decrease. So it's less rigid, right? Okay, when you reduce R by half, how much is the IP change? What's the IP equation? IP equals, for circular, this one. What's the IP? Anyone remember? D 4 pi 32. Okay, now if I change the R by half, how much is the IP change? It's the 2 force power. So 4, that's 16 times. Right? So your IP is going to decrease by 16 times. Therefore, your angle is going to increase by 16 times. All right? Okay. The easy one will be, let's say if I double the G, how the angle is going to change? Half. That's easy, right? Linear relation. The challenge part is here. This is not linear. It's force power. So if I double the area, so I'm square root times 1.4 times the radius. And then how much is the IP change? If if R change to, actually this is not, if A change to 2A, how would the IP change? That means R change to square root 2 of R, right? In other words, it's actually 1.414 R. Okay, so therefore, when you have the RP, it will change square root 2 force power. So that is 4 times. Okay. All right. Okay. What if I do this? Okay. If I change it, make it the bar not uniform, apply a T here. Half is smaller, half remain the same. How much is the total rotation angle going to change? All right. I'll leave that to you. Give me the answer when you come here next time. All right. So I change this part. It's remain as A. This one is A over 2. What's the angle? angle change. Okay. Quick reminder: we have this quiz number 4. All right. It's due tonight. It's mainly have you to get familiar with when you have non-uniform bars, how to determine the internal load here, internal load there. Right. It's due tonight. Oh, thank you.
No problem.
Yeah, you have a question about the quiz? Okay, let's see.
So you said that if we assume
This is for quiz number 4, right?
Yes.
Okay.
if we assume going in,
Uh-huh.
then our answer will become positive because we assume the correct direction.
So basically, if it's tension, we call positive. It's not in. Yeah, it's actually yes, it's in. For the internal force, let's say here, if it's going this way, away from surface, it's tension, right? You try to pull it longer, so that's positive.
Okay.
If it's towards the surface, then it's negative. So for the internal force, when you cut it up, okay, then for the force, for example, this load here, it's hard to say it's positive or negative. But the load itself, it's hard to say positive or negative. Okay. So the concept of positive negative is different from statics. In statics, everything you push this way, you call positive. Go other way, you call negative. That's when you can write equation of equilibrium. That's when how you count it. Now, if you talk about deformation, you have to have one force here, try pulling something. Then that's a positive pair. So this is positive. This is also positive.
Okay.
Okay.
So
This is negative. This is also negative. You compress on something. Yeah.
So
that's a
because
sign.
this is going into the bar. then
Yeah,
the
this is your compressor on the bar.
Okay.
So therefore, you're going to generate compression. So therefore, these two forces will be negative.
Can I upload the homework today? Still?
Upload homework.
Yes, I didn't finish it.
I think the time is like 4 o'clock. 4 o'clock today, right? You're in which session? You're in this
This one.
one. Okay. So this one's supposed to due at 2 o'clock.
Okay.
Okay. Let's say for this one day, if you not, maybe you can you give a paper copy, put it in my office like by 4.
But well, I work until 5 here at school.
Mhm.
Could I do it after 5?
Maybe email by 4.
Okay.
All right.
Okay.
Email to Travis by 4 o'clock.
Okay.
All right.
Thank you.
Depend which quiz you're talking about. Quiz number 4, I think it's due tonight. Yeah, it's due tonight. Actually, I don't. I have a meeting come up at 3. But if you have a quick question or
No, that's fine.
okay, all right.
All right. Hi everyone. So here is a demonstration how a shaft deform under torque. So if this is a shaft, right? So if I apply a torque here at one end, so here's the rotation. Right? So in the middle of this shaft, I draw a few lines. You can see the straight lines and also the line perpendicular that actually represent like a cross sections, right? So the cross sections of this shaft. So when I rotate the shaft, you can see here my hand applying moment. So when I rotate the shaft, you can see the lines along the actual direction. It's getting rotated a little bit, right? So I can rotate either way. So it goes this way. So you can see the line initially is flat, right, horizontal, and now when I rotate, so one end move down, the other end move up relatively. So I can go this way, right? So that's this shaft is under torsion. Okay. However, if you look at these lines, the perpendicular line, the cross sections, right? So when you rotate, you can see the line seems to remain unchanged, right? Where the other line is moving around. the longitudinal line is moving. Okay. So based on this observation, here we have an important assumption for torsion. That is, all the cross-sectional planes will remain as a plane, and we call this a plane assumption. So a plane assumption basically means when a shaft is under torsion, the cross-sections remain as a plane. And specifically, that means the plane remain flat. That's point one. But also, it's like a rigid plane. So it just rotates, right? So it's like my hand. This will be rigid, so it just rotate, right? And it remains the same flat shape, right? But also same geometry. So the shape of my hand doesn't change. It's just rotate. Okay. So the shape and the size remain the same. It's just like a rigid plane that rotates. So therefore, when you rotate a shaft, the planes, all these cross-sectional planes, they rotate relative to each other, but they all remain like a rigid plane. So that's the kind of deformation that occurring in a shaft. And that's an important assumption we call plane assumption. And then we'll derive all the stress and the strain, the deformation, and the relation between the deformation and the torque based on this plane assumption. Right? Thank you.